Сейчас. Well, hello, my name is Maxim Penkin, and I'd like to tell you about the scale recurrent network for deep image deblurring.
Could you please turn on your camera if it's possible?
Sorry, I forgot. Hello.
Okay.
Так, поехали. So, I will give a small introduction to the topic as the first slide. Image deblurring is an important problem in computer vision and image processing. And the task is you have the blurred image as an input, and the goal is to recover the sharp image with the details and structures and so on. So the traditional methods without any learning, of course, exist, but they require strong simplifications. So they require the simplified assumptions, and the real-life performance of such methods is not so good. There are such artifacts as ringing and overshooting and so on. So here deep learning methods help, and nowadays there are a lot of articles about such models of deblurring, for example, and I would like to discuss one of them, which is called Scale Recurrent Network for Deblurring. So here we see the proposed by authors architecture. It is the so-called cascade architecture, which is composed of 3 units. So here 1, 2, 3, and each unit model processes the image in different scale. So here is the same image, but in different scales. The first key point of the architecture is using shared weights between the levels, between the scales. And the second key point is using the recurrent mechanism in the bottleneck. So the recurrent mechanism through the bottleneck, which aggregates global features through different scales. So here is the formula of the whole network. We want to get I large, it is the resulting sharp image, and here is the auxiliary output H with index I, it is the bottleneck value from the current scale. And we feed into the network these values. It is the blurred image at scale I, the previous result upscaled, which is concatenated here, and the bottleneck here, which is passed to the recurrent mechanism. It is the LSTM here, but authors tested different versions of recurrency, simple RNN, LSTM, for example. They chose LSTM as the best one in terms of visual quality and standard image metrics like PSNR and SIM. And theta is the parameters which are shared across different scales. So some words about why they use shared parameters. First, it is intuitively a natural choice because at each scale we do actually the same. It is the first. And the second term is that if the parameters are not shared, it is the concern that the model will overfit to a specific scale, for example, or to a specific motion. So they decided to share parameters here. Then about training procedure, they use a simple L2 loss. Kappa is, kappa is the weights of each scale, n is number of scales, it is 3. Then it is the output image, as I said at the previous slide, ground truth image. So they also tried in their experiments adversarial loss. So they put additional discriminator to the model, and they use a combination of regression loss here and adversarial loss. Then the inputs for the discriminator were CNN output as fake one and ground truth image as real image. But they finished their article with this simple loss. They said that it gave the best performance. They use Adam optimizer with polynomial decay with power 3 to get as accurate extremum value as possible. The patch size is quite big. We use GoPro set, and the size of input image is 720,1280, and the patch size is quite big, I suppose. So here are the results. Here are the results. There are, Here are the results. Here are 5 models. SS model is a single scale model. Then SC model is the cascade of 3 nets, as I said, 3 U nets, but no sharing weights. It improves, of course, the performance in terms of Pearson metric, but we can improve the performance more if we introduce sharing weights. So just using sharing weights helps here. Further, they add recurrent mechanism here to the cascade of 3 U nets, and the performance improve even more. And the last one, is, I think, the minor experiment just to prove that U-net structure is valuable. So here is the single scale model like the first one, but with no max pool layers in encoder and deconvolution layers in decoder. So just the sequence of convolutions, flat structure, yes. So from this table, we can see that the best performance is the best performance provide the proposed network, the cascade of 3 U nets with the current mechanism, LSTM version. And the final slide here, just to check the visual quality. The first column is input image, and the last column is the output result. So we can see that the numbers are seen good, no color artifacts. So it is a good one. That's all. Thank you for attention. If you have any questions, let's discuss.
Okay, the first question about the generalization ability of this model. So it seems like you may overfit to a particular type of deblurring in your training set. So if you consider this training set, you are able to restore from this type of deblurring, second data set, second type of deblurring. What about the situation when you train on one data set on one kind of deblurring, and then try to apply this model to a different data set? What can be said?
They didn't check it, but GoPro set has the different type of blue. So I think that the generalization can be, because the type of blue is really different in the GoPro set.
So they have used, well, a wide range of situations of lighting, I don't know, of moving, of shaking, etc.
During training, they use, of course, the augmentation, some standard one, scaling, for example, rotations, and so on.
And what about blurring augmentation? No?
No. This was just from the data set, because the data set, they say, is quite large and different types of blur exist. The augmentation of blur, they didn't do this.
Okay. And what about the testing time? So if we are trying to apply this to real videos, I don't know, it seems like if we do image-wise all the processing, everything would be quite long.
Yes, I worked with this module some time ago, and the processing time is totally not real time. So yes, it is an issue. So it is. I think that this model is not proposed for the real time performance. It is just the article for the scientific purpose.
Okay. Any more questions?
Okay.
If not, thank you.
Thank you.
The next speaker would be Kaptelov Dmitry.
Hello.
Hello.
Yes. Can I start?
Yeah, please.
I'd like to tell about relation GAN for text generation. First, I start with disadvantages of previous approaches to generate text through GANs. The first is that their performance is quite sensitive to random parameter initializations and mode collapse. Also, we have text, it's a sequences with discrete data, and we need somehow to differentiate our outputs, and previous approaches use the reinforce for training with discrete data with big variance. Also, usually with reinforce here came different array heuristics that making already difficult GANs more complicated. Also, there are the problem with mode collapse. It's because a lack power of generator. And short review on the Railgun. It has three main parts: relational memory-based generator, instead LSTM that's usually used in GAN, and Googles of max relaxation instead reinforce, and multiply embedded representation in discriminator. And also showed that each part of this part plays an important role in performance of network. And they stated that this GAN have ability to control the trade-off between sample quality and diversity via just one hyperparameter. Let's look closer on all parts. First, start with the relational memory-based generator. Some words about problems of LSTM as generator. The first is that discriminator slows very quickly goes to near its minimum, means that discriminator usually more powerful than generator. It's because of lack of expressive power of generator. Also, this reason causes mode collapse. And there's a problem with generation of long sentences because LSTM pack all previous information in one hidden vector, and usually it's not enough to model the long dependencies. And take a look on relational memory. We have memory matrix where each row is something like memory slot, and we have embedded input, and using this memory matrix embedded input, we get queries, keys, and values for self-attention with h heads, and after self-attention we get new updated memory, and using this updated memory and the current memory matrix, we can get next step matrix, memory matrix, and output by using two functions. Let's take a look on Google softmax relaxation. There is approach that usually we sample output from softmax of logits, but we need somehow differentiate it, and we use relaxation. Google softmax with parameter there is a inverse temperature, and we can control this temperature, and if this temperature tends to infinity, it means that we have a better approximation of argmax, but we have a big variance of gradients. And it's our intuition that big beta causes poor SAM quality, but good diversity. And on other hand, small b beta causes mode collapse, but good quality. And also decided to use such exponential policy for beta is that beta changes from iteration to iteration, from 0 or from 1 to max value. And big it's total number of iterations. And it stated that we can control our trade-off between sample quality and diversity by choosing beta max. Some words about discriminator. Usually in GANs for text generation, we use CNN-based classifier as discriminator. We also use this classifier, but we used in for S states. Each state is get from using embedding matrix for each state, and we get as representations of our output, and we pass it through discriminator. It's one discriminator with sharing weights, and compute S losses. And we passes our real input, generated input, and in general get such a loss function. And in work also decided to choose such function. It means that log sigmoid between output of discriminator for real image and generated image, and its loss somehow estimates the probability that real sentences are more realistic than generated. And also one technique that also used is that generator was pre-trained on MLG task. About experiments of authors, they first experienced with synthetic data. It's 10,000 of sequences generated by an trained LSTM. And they use such metrics, negative likelihood, one is expectation of generated over real image, over real sequences, and one other NLL oracle is expectation over generated. And the idea is that first measures sample diversity, and the second metric is measures sample quality. And they calculate this metric with comparing with other approaches with this loss and shows that it outperforms others. Okay. Also, they follow charts for different beta and with analogy and oracle losses for different beta. And we can see that if we increase Bmax, NL gen decreases. It means that we get a better diversity. And if Betamax decreases, we get a better sample quality. And this is absolutely corresponding to our intuition here. So where we said that big B causes good diversity and small b causes good quality, we showed this in experiment. Okay, and they also tested on the real dataset, captures dataset, and we can't use an oracle because we don't have access to the generative network. We, for test data, we have only samples, and they used blue scores. And the idea is that for each generated sentence, we compute blue score if all test samples are the reference, such a way. And some additional research also showed the importance of each part. There is an impact of relational memory. They compared the relational memory generator with LSTM with higher dimension Lucid2 with 32 as generator and 520 12. And the idea is with 32 hidden dimension, it's usually used in previous GANs, and with 512, it's have the same hidden parameters as relational memory. And relational memory outperforms both these generators on blue score. Also, they compare reinforced approach with Gumbel-Softmax approach and also shows the outperformance. And they show the impact of their discriminator is that if we increase the number of states, we actually decrease the loss and increase the blue metric. So thank you for attention.
Okay, thank you. Could you please speak a bit more about the problem itself you are trying to solve? Why do we really need to generate some text? What kind of practical problem we are trying to solve here?
There is a task of text generation, and GAN is trying to solve this task. Why actually people do it for some
But we usually generate some specific text, like, I don't know, we start with some text and then try to continue it. Or we usually not interested we're not interested in generating just some text.
Okay, I don't know maybe a real field of it, but maybe for training itself. People do it, I don't know, for mm, for showing the ability of networks to do this.
Okay, what type of training data set did they use? Wikipedia or what?
Training data set. Or this part, or I forgot.
Okay, so you have concentrated only on the mathematics, only on the model.
Yes. Such way.
Okay, could you please return to the discriminator structure? Yeah, here. So we have a text sequence as an input, and what we have as an input to our CNN. We take like a window of
no. It's an embedding matrix. It's we have input.
Embedding matrix for the whole sequence or for each word?
For each word, we have t times v, where is vocabulary, and for each word, we get embedding and get t times d matrix.
So, and we compare, so for each word, we calculate some score, yes?
And no, for each sentence. For each representation of sentence. We have S embedding matrix. S is parameter for states. It could be one.
And how you move from representation of a word to representation of a sequence? Just concatenate all these things and use it as an image, or what?
I don't closely look for based CNN discriminated, but I guess it's could take all sequence of size t times d.
Well, you know, it's you said that this is a standard thing to use a CNN-based classifier for the case of texts. It's a strange statement because we always say that if we need to deal in our neural network with sequences as an input, we use a kind of recurrent neural networks or transformer-like architecture. And here you say that no, the standard way is to use a CNN. So now I'm trying to understand how you actually transform your input sequence to the input to the CNN.
Okay, no, in such a way we get t times the input, and then it's passed to CNN classifier, and then I believe to also that it works.
D times D, where D is a dimension of embedding.
D is the dimension of embedding matrix, yes.
So D times N times number of words.
Yes, T, I mean the max sequence length, yes.
So you just said take a set of embedding for each word, then concatenate them in one, say, image, and take it as an input to a CNN, yes?
No, I don't understand. Maybe the input is T, it's for sequence length, and V for vocabulary size. Next, we pass it to embedding matrix and get embedding for each word, get T times D matrix.
Yes, that is what I'm saying, that you actually construct an image from these embeddings for each word. Okay, I understood. So people, any more questions on the talk? Okay, if no, thank you.
Thank you.
Now let's move to the next speaker, to Ivan Sayenko.
Is everything okay with sound and video?
Yes.
Well, I believed I could turn on the camera, but it doesn't seem like I can do it. Sorry for that.
And could you please increase the sound, because
Yes.
now it's too. We're hearing you not very good.
Can you hear me better now?
Yeah.
Okay. Well, I'd like to tell you about a neural network which is called Luke, about entity representations with entity-aware self-attention. So what's going on? Usually we try to understand language. When people understand language, it means that they can match words with its entities. Entities — это сущность. So, but usually neural networks learn just embeddings for words, and it doesn't really lead us to some understanding of language. Of course, there are some models which try to learn entities, but usually it's just like we learn fixed embedding vector, and there is a base of these vectors. And of course, we can't use entities that don't exist in the base, and of course we need to somehow link entities to what's going to the words in the text. Of course, there are some contextualized word representations, BERT and all other networks after that. And of course, they provide some word representations, which are pretty good. And the authors of the article decided to learn RoBETA just like it was learned for words. But now not only for words, but words and entities. So here is the scheme of this net. There you can see vectors for words and vectors for entities. So we compute representations as intermediate, as output for all the tokens using this transformer. And of course, we can predict the things that were masked with special symbol mask. Okay. How do we represent all the stuff? The first one is token embedding, which are different for words and entities. Of course, we have much more entities than words, so we need. So the authors decided to use special to use two matrices to get full one for entities. Well, and the other ones for position and entity type are just 1D vectors. So we have, so using these things, we can get representation of a word and entity. For a word, these are two first embeddings, and for the entities, all of them. Well, of course, there is a usual. We know special usual formulas for self-attention, which were used in articles earlier. Now the authors decided to use some special entity-aware query mechanism. They calculate ease with a different way. They use not one matrix Q, but 4 ones for all the possible situations with words and entities. And they state that the computational costs of the original mechanism and proposed one are identical, except the additional costs of computing gradients and updating parameters.
Well, Ivan, could you please give an example of entity? What does it?
For example, Los Angeles, as it was stated in this example. So you see that the authors trained their model on Wikipedia. So every Wikipedia article can be an entity.
You mean the name of the article?
Yes, yes.
So we usually have for a particular text, we usually have like one entity or something like this.
You see, no, I mean that there can be different entities in the sentence. So everything, maybe not every noun, but nearly all of them can be entities. So,
like links to other articles in Wikipedia. Okay, I understood.
Yeah. So, well, in training, that's exactly it. These were links to different articles.
Okay, continue.
Well, some words about pre-training. You see that the authors used such a scheme like they train the base network, and after that, after training this one, they train more on special tasks, or some different tasks, which I'll talk about a bit about it later. Well, the first one, pre-training task, is the task where we replace a certain percentage of the entities with special entity mask, and of course we try to predict it. Yeah, it's written there that hyperlinks are entity annotations. So there are formulas which are used for predictor with a special nonlinear function GELU. Well, and in the end there are results for experiments. It should be noted that, for example, the first task is entity typing. What's going on? The task is pretty similar to the first one, but now the score uses only the type of entity. So in the data set there were 9 types of entities, and the task for the net was just to predict the type of it. But there are some harder problems which this model can solve after some more training. For example, these are closed-style question answering. So how does it work? There is a sentence. There is one word which is thrown out in the end of the sentence, and we need to predict which word it is. Well, one more thing that I have noticed is that nearly all the data sets which this model gets state-of-the-art results are, to be honest, Wikipedia sets. And as we know that that the model was trained on Wikipedia, I don't really know how to treat that, but that's a fact. Well, I believe that's all for my.
Okay, thank you. So the first evident question, why do they use a special activation function, this GLU? Because in activation function, we usually are aware of the calculation speed. And if you move to YARF, it's not so quick to calculate.
Well, you see, in the article, that's not described at all. So
not described at all. They have used a very special activation function and say nothing about it.
Well, I've just opened the article and what's written there? These vectors are bias vectors. GLU is GLU activation function. That's all.
Maybe they have a link to another paper where people also use GLU. That is why they use GLU, no?
No, there is just link for the article where GLU was stated.
Okay. And one more question is about these actual entities. It seems like the structure of the model is the following, that you just have two types of words here. So if you have, say, 3 types of words or 4 types of words, you may use a similar model. What are special things about thinking on the second type as entities?
Well, if I understood correct, you say that we can just we can just use in entities some word combinations, right? So
we may say that, let's say that our words have, I don't know, 3 types, and we read them as these 3 types and try to forecast, say, a type of a word for a new sequence. So it's nothing special about that we treat some type of a words as an entity in our model.
Yes, you see, first of all, if one word is just an entity, it there are 2 vectors for it, one as a word and one as an entity. So yes, that's true. When we talk about some entities which are longer than one word, we just well, okay, it's how to describe it. So, well, the shortest answer is really yes. As I believe, I start to think if the authors could just not use special representations and all the stuff for entities, but I believe it just helps sometimes.
Okay. Any more question, people, about this paper? Okay, then thank you. Well, let's move to this to the next talk. Alexander Ustюжанин.
Отлично, я замученным был. Вот теперь меня слышно?
Yes.
Okay, let's begin.
You also don't have a camera?
Yes, my laptop doesn't have operation system right now. Windows deleted my Linux. Yes, very good at.
And how do you use your laptop without operating system? By the way,
that's why I don't. I have a stationary PC.
Okay.
Without camera. Yes, I love Windows. Okay, let's begin. Hello, my name is Ustюжанин Alexander, and today I want to tell you about applications of deep learning for navigational tasks. So let's begin with some definitions. INS, which is Inertial Navigation System, is a navigational device that uses a computer, motion sensors such as accelerometers and gyroscopes to continuously estimate position, orientation, velocity of a moving object without the need of external references. And here are some examples of external references. This could be an optical recorders like digital cameras, depth field sensors, for example, which are already built in modern smartphones. This could be a GPS tracker widely used for car navigations. Another example could be special motion capture studios. They include many special sensors that are placed all around the room. Its purpose is to record labeled dataset. By labeling, I mean very accurate pose estimation. Also, external sources could be even the described IMU modules, but placed outside the mathematical model that are not considered. Sensor fusion is a combination of sensory data derived from disparate sources in such a way that the resulting information has less uncertainty that it would be possible with these sources if these sources were used individually. So that means, for example, if we have an IMU module, which tells us acceleration, angular velocity, and the digital camera, which recognizes features from image frames and estimates of our movement parameters. So the fusion should produce better estimations than IMU or this digital camera individually. But why doesn't it always work? For example, GPS might be unavailable or highly imprecise indoors. For example, if we walk outside, inside a building or going through the underpass. Another example could be lack of valid features in visual context. For example, if we go inside some poorly illuminated room, very dark room, it lacks any features. Camera, regular digital camera won't recognize anything. Another example could be a monotonic environment like large white wall, which doesn't contain any features at all. Also, another interesting example is that visual context of environment could be deceptive. So what does it mean? It means that those sensors, like for example, IMU and camera, do not correspond to each other. If we enter an elevator, our visual context will estimate that we don't move. If we, for example, film doors of our elevator, but inertial model will detect acceleration of elevator, especially in the moment when the elevator start moving. There are many other examples, like for example, if we walk in a shopping mall, there are many escalators. So here's the same. Escalators move without any acceleration, with almost constant linear velocity. So that means that our IMU model won't detect any acceleration, but our camera flow will produce non-zero transition, and that will break the sensor fusion process. Pedestrian data reckoning is the process of calculating current position of self-moving object by using a previously determined position. Estimations of speed and heading direction adopted in the field of pedestrian navigation with handheld devices, for example, our cell phones. Here we can see this scheme, which demonstrates an order in which all data is being processed. The scheme represents PDR solution in modern day understanding of navigational problem. So first of all, we should classify our type of motion with motion mode classifier, because running and walking with normal speed drastically changes our biomechanics. Then we should estimate our length of a step, which again depends on the type of our motion. Detect each step, integrate angular velocity to acquire heading estimation, and in result, we update our pose. So that is a quite sophisticated approach. Let's see how conventionally it was solved. So it really depends on our humans' motion biomechanics in a way that we can interpret acceleration curve on different axes. Here we can see that for human, in order to make a step, we should lift one of our legs, swing it forward, stop the swing, and touch the ground. So modern day accelerometers update about 250 times per second. So that should be enough to detect all of these events. And here are simple formulas that update our pose. Psi is acquired, like I said, via angular velocity integration. S is our estimated step length. Each step is separated using different peak detectors that depend on acceleration amplitude. And here we can see how this step length is being evaluated. Here are two main approaches that was proposed a while ago in 2002, I believe. So these are Weinsberg and Kim's approaches. These formulas are obtained empirically, so there are no particular sense in these powers of 1/3 and 1/4. And in both methods, acceleration statistics have been boosted via gain values, which are our prior knowledge for each motion type that we detect. Like again, this approach is very old, so let's see how we can. We see that this model won't produce any stable results. Let's see what we can do with deep learning approaches. Current paper considers two approaches to regress the user change in distance in proposed StepNet. First is fixed time windows, regardless of the step duration, where the raw IMU data is passed directly to the network, which corresponds to a method called distance change estimation. And second is varying time windows aligned with the step duration, where features are calculated on the raw IMU measurements and are fed to the network. And this corresponds to two other methods, which are step length estimation and PDR's gain estimation. So let's focus on step length estimation. It considers similar pipeline as PDR scheme that I showed before. Let's examine it step by step. Step detection remains the same as in deterministic PDR based on magnitude acceleration value. There are a couple of modern approaches of doing this, but this task is not considered by this paper. Another thing is that orientation estimation. Orientation could be estimated via Kalman filters integrations. It's widely used for this approach, but again, not main concern of this work. Main concern of this work is the following. For example, smartphone location recognition step. This paper proposes 4 main types of motions. There are texting mode, which means that the device carrier holds its phone normally like we do while texting. Talking, which means the phone is close to our ear, etc. So they employ a one-dimensional convolutional network and an LSTM in an architecture that combines both of them. There are many papers on 1D convolutional neural networks for human activity recognition, so it's quite a classic approach. The motivation for such architecture lies in the fact that CNN has the ability to extract features from the data, while LSTM can exploit temporal dependencies in the time series problem. Here's the feature extraction step. We calculate our main 8 axis features of acceleration and angular velocity, and also which are axis and angular velocity along its axis and norm of vectors. And also we add various statistics like mean, standard deviation, mean absolute error, mean max values, g-crossing, etc. Maybe it's worth noting what g-crossing is. G-crossing rate represents how many times in a certain window norm of our acceleration crosses value of 9.81, which is acceleration of free fall. And let's move on to step length estimation. It's a typical CNN-based architecture that's considered for this task. The input to the first layer is C1 is the features calculated on the sensors measurements. It has 32 units with real low activation. It's not really important the parameters of these layers. So the main thing that we pass our MU measurements through several convolutional layers, dense layers, and that produces estimations of step length and optimize it with mean square error with any other stochastic algorithm. So classical CNN approach. So here we can see the evaluation metric, which is distance error metric for step length model. It's not particularly interesting, just the way they compare the results with another methods on the same data set. So in conclusion, deep learning based PDR is approximately 10 times more accurate than conventional one. It's worth mentioning that this PDR approach is only one small step in 100 others. Of course, people use different sensor fusion techniques, build simultaneous localization map, constantly optimizing predicted trajectory in real life, do loop closure, and many other techniques. And today I just wanted to mainly present you that such tasks of navigation exist. It's an active research topic because all of these techniques are used, for example, for artificial reality engines. It's a very difficult topic actually, in the sense that there are no mistakes allowed. Systems should work and estimate human pose faster than 0.04 seconds. Otherwise, a person will feel dizzy, what is called motion sickness. You may have heard about this problem in VR headsets. So this is just how human nature works. And if we, during our time series, only once falsely estimate our orientation, the trajectory will move in the absolutely opposite way. And after this, we can throw away our cell phone because we don't need it anymore. There have been one mistake and it's completely ruined a whole trajectory. So that's the problem in this topic. And here are some references, and thank you for listening.
Okay, thank you. I would say that estimating the velocity of a human in real cities is actually a very important information for cellular networks. For example, if a cellular network would know your actual speed, it may sufficiently increase the speed of an internet on your phone, the quality, because it may choose the corresponding frequencies and other parameters for cellular networks in a much more efficient way. So the question here that you said about a human motion when just the person walks along the street, say, but what about a more general motion, like a person moves, then, I don't know, move to a car, moving by car, then maybe by bicycle. May we solve such a general problem of velocity estimation?
Yes, there are currently papers that considers different motions like this. You're absolutely right about the importance of this problem, because we can talk, for example, about Yandex Navigator, which absolutely doesn't work if we go into underpass or we walk out of the subway. And there are, for example, 8 exits, and we don't know where to go. And in this underpass, there is very poor internet connection, and Yandex Navigator, relying only on IMU acceleration and gyroscope, absolutely cannot navigate us, because it simply doesn't work without the internet. So that's the big problem. And answering about different motion types, for example, if we are on a bicycle, going to the car, going into the car may be considered as a pocket motion. Pocket motion are considered by many papers, which means that we put our cell phone inside our, for example, pants pocket and move along, and it should work in many other papers. It's a very difficult task of classifying different motions, but there are actually another 4 classical motions, not like this. First classical motion is walking with cell phone in hand, normally like texting. Second is calling someone, like keeping our cell phone close to an ear. Third one is cell phone inside the pocket or a bag, handbag. And fourth one is placing our mobile phone on some, like for a bicycle. So it's some, how to say it in English? В общем, на тележке такой. Я даже не знаю, как это называется на русском. Yeah, so there are 4 these main motions that I think can describe many of our lifetime activities. Like, for example, yes, keeping our cell phone inside the pocket or riding a bicycle. That should be the same. And there are also some experiments comparing with some robotic hand. What is called robotic hand is like stationary, small flying vehicle with Z-axis stabilizations. So there are no noises of our human. For example, our hands are shaking. If we walk, there are constantly Z-axis acceleration, like sinusoid, and this is not recognized by models which are trained on this robo hand, because there are many natural specifications to human biomechanics. Yes.
Okay. Thank you. Some more questions to Alexander?
Okay, thank you.
No questions. So now I suppose to make a 10 minutes break. Let's relax a bit, and then we will have 3 more talks. So we continue at 12:10. And our next speaker is Evgeny Kolmogorov. Please.
Okay, do you hear me and do you see me?
Nice. Finally, somebody have working web camera. Great.
Okay. Now I demonstrate my screen.
Okay, let's go.
Okay. I would like to tell you about lightweight three-dimensional human voice estimation network with training using teacher-student learning. Human voice estimation play an important role in understanding people actions and have some attention from computer vision community in last few years. Algorithms that solve this problem should create a three-dimensional spatial model of skeleton where each key point is some joint on human body, and you should get some relative positions of these points. This task is very popular and can be applied in different areas, such as sport analytics that understand sportsman actions. Such types of algorithms can be applied in augmented reality systems, and you can use these algorithms that create virtual scenes in creation movies and computer games. Nowadays, there are two main approaches that get pose estimation. The first way is to use special devices and hardware like Microsoft Kinect or Intel RealSense. The main advantage such approach is that they have enough good quality of prediction, but they have two main drawbacks that you should spend money that buy this device, and they work bad on open air. And the second way is to use deep learning algorithm from a simple camera. This have main advantage that you shouldn't buy anything, but the main drawback that time of prediction enough big. You should have a GPU that have less time. Authors of this paper try to speed up predictions of pose estimation and incorporate these predictions on mobile phones. Okay, I will start with model outputs because it will be more understandable for you. Here we have 4 tensors for each key point. First tensor is heat map joint on two-dimensional image, and other tensors x, y, and z show deviation point from root human from root point. As a root point was taken center of body. And when they get of precise position, they found maximum in H map and take this point from other 3 tensors. Here is depicted model architecture. They use MobileNet as encoder and have 2 ResNet-like blocks. After these blocks, they split output on 2 branch. One upper branch, they compute standard evaluations with 128 channels, but on lower branch, they compute special tensor by convolutions which show deviation from parent point. You can imagine human skeleton as a tree, and you can use parent and child relation. And also they compute distance key point from root point. This here is depicted mobile net convolutions, which speed up time of prediction and decrease memory consumption. Here we have one convolution kernel, and this convolution kernel applied to each channel. After that, this feature maps concatenated, and after concatenation, they apply pointwise convolution. Also, authors using distillation approach, the main idea of this approach is that they have two networks. The first network is teacher. Teacher network have more complexity than student network and have much more training parameters. They use as a teacher network model with such architecture, but instead of mobile net, they use ResNet. As a student network, they use mobile net version. During training, they use teacher network outputs, but when they predict polls, they use just student network, and such approach get some benefits. Here is depicted loss functions that they use. They use loss function between heat maps on two-dimensional image, simple L2 norm with distillation parameter alpha. Also, they use between key points location loss, and they use also distillation parameter alpha, and they use heat maps predictions as weights of weights. Here is results which can get authors. As you can see, here two equal columns in the bottom. First, two equal rows on the bottom. First row is training without teacher model, and second row is training with teacher model. As you can see, authors get some profit when they use teacher model. As you can see also that quality of prediction is not best, but if you see on column with number of parameters, you can see that number of parameters is much less than other approaches. Here is number of frames on each devices. As you can see, number of frames can afford to work this method on mobile phones. They use mean per joint position error. This equivalent of MSE, but also apply mean between joints. Here examples of model predictions. As you can see, model produce not bad predictions. Here much more the most hard cases this model. The first case is crossed knees before, because woman with skirt. And the second error because specific pose position. And results which can get, the first, the proposed method show fairly good quality of prediction three-dimensional pose. And among all available methods for evaluation three-dimensional human pose, this method has the fastest prediction time and the smallest number of trainable parameters, which allows it to work on many modern smartphones. And this method was one of the first methods that use knowledge distillation. That's all.
Okay, thank you. I have a question about training data sets, how they actually get the true annotation, the true skeletons.
They use specific devices on human body, and these devices read the position.
So they have a Kinect that measures the heat map, the depths, yes, and also the skeletons.
No, heat maps, this simple regression problem like detection.
Yes,
you can use.
But in order to, so these heat maps, the transformation from input image to this heat map, how do they train them? Using the Kinect data?
Honestly speaking, I don't see how datasets look like, but I think that they have, as you say, Kinect data, or they can label points by humans.
Okay, and maybe you know, in last models of mobile phones, like in last iPhone, don't they have a depth camera?
I don't know. Maybe a last version of such phones have depth camera.
Yeah, because it seems like that modern phones or the next generation of mobile phones would have such type of camera, and we actually may use depth information in our algorithm.
Yes, maybe it get more quality, increases the quality of algorithm if we use depth channel.
Mm-hmm. Okay. Any more question to Evgeny? No question. Okay. Thank you. Let's move to the next speaker, Maxim Nahodnov.
Hello?
Yeah, we hear you.
Can you see my screen?
Yes, we can.
Okay, today I would like to tell you about paper unsupervised learning of probably symmetric deformable 3D objects from images in the wild. The main goal of this paper is to recover 3D image of some 2D image, 2D RGB image. So
2D. Why 2D?
2D, sorry. First of all, I would like to cover some possible applications of such technologies. First of all, it's 3D modeling. The topic of this paper is exactly 3D modeling from the 2D modeling. Next area where we can use such type of algorithms is deepfake technologies. Next big area is augmented reality. So we often don't have some expensive lidars or depth scanners, so we only have access to two-dimensional images, and we would like to recover the 3D model of the space in which that image was captured, or recover a 3D model of some captured objects. So the replacing expensive lidars is one of the biggest profits that we could have from such technology. So there are key features of this paper. First of all, this novel method takes no additional ground truth information. So we do need to mark our data in somehow, for example, we don't need to have some depth information. We don't need to detect some core points or something like that. We took ordinary two-dimensional RGB photos of some objects and recover the 3D map of these objects. Also, we can apply such method to any data set of single view images. So we do not require multiple views on the same instance. It's very important because in real life, it's very unusual to have multiple image of some instance from multiple views. So, and the last and the key feature of this method is to exploit bilateral symmetry. So most of objects on our planet, handmade or natural objects, have bilateral symmetry. It's something that we can use without any precondition. So we can take any object and with big probability it would have bilateral symmetry. So we can exploit this knowledge. So now I want to tell about the method. As I said, we will use bilateral symmetry. Also, the main idea is to disentangle some basic qualities of the 3D image. First of all, it's depth map. Depth map is one of the key features of 3D recovering task. Next feature is albedo image. So it's like a synonym to texture image. Then we must recover illumination. By illumination, we will mean some vector from that light is coming to the object. And the last but not least, the viewpoint. It's some encoded transformation which can transform canonical instances of deep map, albedo, and illumination into the observed image. So our goal is to recover canonical instances of depth map, albedo, illumination, and recover viewpoint that encode some information how these canonical instances can be projected into original RGB image. So then we would like to reconstruct original 2D image from those quantities, like I said before, DeepSmap, albedo, illumination, and viewpoint. And we can use autoencoder-like model to train end-to-end model to recover these quantities. So I think on picture it would be more clear. So as an input, we take 2D image. Then we recover somehow with encoder-decoder-like structure DeepSmap, albedo map, lightning vector, and viewpoint transformation. Then we can combine all this stuff into some renderer that would give us a reconstruction image. And then, like an ordinary autoencoder, we can use reconstruction loss to train our model end-to-end. What's also important in this work? As I said before, we deeply use bilateral symmetry. What does it mean? It means that we could augment our images with flipped copy of such images. So with use a precondition that every image in our dataset have some horizontal line that we can flip around this line and get very close to the original image object. And from this pair, we can recover dips, albedo, light, and viewpoint. So flipping around some axis of the symmetry, we can get like a fake capture from the different angle. So this is the main idea of this paper. So now get into details. Let I, a hat, and a hat with cross the original image, recovered image, and the flipped recovered image. Let A be albedo map, D dips map, V is a tuple of 3D vectors that encode information about original viewpoint and vector to the from the original viewpoint to the center of the object. And L is a vector on the unit sphere that encodes information about light direction. So we can reconstruct our image from albedo, dips map, viewpoint, and light source direction in 2 steps. First step, we took albedo, dips map, and light point and recover texture information. I mean, we recover brightness of each pixel of our image. And then we use some camera-specific information to project our texture into original 2D image. Also, we could apply same type of transformation to the flipped instances of albedo, dips, light, and viewpoint. And then we can construct reconstruction loss as a sum of reconstruction loss for the original image and for the flipped image. So we use the second term in this loss to ensure the symmetry condition. So we ensure that if we flip image, we can recover from this image original non-flipped image. So we believe that such type of loss can ensure that strong conditions that we that we use in this method. So how we compute losses? First of all,
already 10 minutes passed, so please come to the end quite shortly.
Yes. We use some fully factorized Laplace loss as discrepancy between image, and we use Gaussian perceptual loss using pre-trained VGG model. So also we use some confidence maps that we also predict with our end-to-end model. So how we reconstruct image? As I said before, first of all, we reconstruct texture with some Phong model. It's the basic, one of the basic models that only use normals to the surface of the 3D object. And we use some well-known facts from the projective geometry to recover a projected image. So go to the results. One of the hardest problem of such tasks is to measure the quality of our reconstruction. There are some data sets where DIPS information are given, so we can measure the reconstruction loss between predicted DIPS map and ground truth DIPS map. So authors compare their method with some baselines, and it performs quite well on the level with some SOTA supervised method. So go to the images. On the left, you can see input images, then SOTA supervised images, and images obtained from the paper. So as you can see, that method could perform even better than state-of-the-art supervised model. So there are some another samples from the model. As you can see, reconstruction performed quite well, and some images of the cats. So I think that's all. Thanks for attention.
Okay, thank you. Once again, a question about training data set. How do they actually estimate the true albedo images?
Estimate what?
True albedo images, reflections.
So they use as a data set like Celeba. It's just
okay. Yeah. I mean, this true information about depths, about albedo, about light.
They don't use such information. They use only 2D images. That's all. It's the main feature of this method. It's fully unsupervised.
Fully unsupervised.
Yes.
And how and now once again, and how do they actually estimate these depths, for example, without knowing about the true depths?
Well, the surprising fact that model can learn all the things just by given an algorithm to recover original image from the depth, albedo, light, and viewpoint.
This is due to the rendering properties.
Phong model to recover textural information, and we give some basic geometry facts about projecting 3D images onto plane. And that's enough for model to recover very good DIPS maps, textural information, and so on.
So very interesting. I think that this is due to the render properties, because in order to generate a good output, you need to input to the renderer something that is quite similar to the depth image, to albedo image, and something like this. And that is why model is able to learn this information from data.
Yes, but I must point out, renderer and projector part of the renderer is also fully unsupervised. There are no trainable parameter in projector. It's just some transformations that project 3D image onto fixed plane.
So this is not the true renderer. This is just something that is handwritten.
Well, it's yes, it's handwritten, but it's nothing like geometry effect. It's some transformation over deeps, albedo, light, and viewpoint that gives us projected 3D object onto a plane.
Mm-hmm.
There is no parameters. There is no
Yeah, for sure, renderer have no parameters because it just constructs the output image from the input information.
Well, projection performed with no error. It's just a geometry transformation. The only error we have in renderer is simply the simplification of the lighting model. We use very simple light model. We don't take into the account some shadows, some second order terms. It's a very simple first order model. But in the projector part, there is no error. It's performed
Okay, yeah, and I understood. Any more questions for Maxim? If no, then thank you. Let's move to the last presentation for today. Olga Tashova, please.
Okay, so good afternoon, everyone. Just a second to share my screen. Okay. So, is the screen visible?
Yes.
Okay. Now I have no clue how. Okay, I'm gonna turn on my video camera now and then share my screen. So, screen sharing. Here we go. So today I would like to talk about a recent paper titled "Your classifier is secretly an energy-based model, and you should treat it like one." So to give some sort of an introduction, first I would like to talk about the differences in modern day deep generative models and classification models. So the initial idea behind the generative models was to was for them to be able to solve the discriminative tasks better than the discriminative models, because the generative models could, for example, input the missing data or perform better on semi-supervised in the semi-supervised learning settings. However, modern day generative networks have diverged far from this approach, and mainly they focus on producing samples of better quality. And their architectures between their modern day generative models and discriminative models, if we talk, for example, about image generation and image classification, are very different. And that is why if we, for example, take a generative model and ask it to perform image classification, its performance is way worse than that of a discriminative classification model. So in terms of the probability density function, the generative model operates with the joint probability and the discriminative model operates with the conditional probability density function. So, and the main idea behind the presented in the paper is the possibility to reuse an existing image classifier to define a generative model. So, and this is achieved with the help of the energy-based models. So I would like to say a few words about them. So within the concept of an energy-based model, any probability density over some real set can be expressed in terms of the energy function of the exponent of some energy function divided by some normalizing constant. In fact, this distribution in physics is often named the Boltzmann distribution, and in physics it is used widely. And the normalizing constant, z of theta, is most times very hard to compute or even to reliably estimate. Because of the probability density function defined with the help of an exponent of the energy function, we can express the derivative of the log likelihood for a single sample this way. So this is the expected value over the probabilities minus the gradient of the energy function. In order to compute the derivative of the log likelihood, we need to somehow compute the expected value here. And this expected value is actually hard to compute because we do not know their normalization constant. And that is why we compute such expected value with the help of the Monte Carlo methods. More specifically, we use Langevin dynamics in order to sample from some distribution, and afterwards we just compute the mean over the samples. So the Langevin dynamics scheme has the following structure. First, we sample some initial value of x from some distribution, and after that we iteratively update the value of x through the following formula. So the next x is actually the previous x minus the gradient of the energy function multiplied by some scalar alpha over 2 and some stochasticities added into the computation of x. Here we introduce a random variable epsilon, and such random variable is usually sampled from the normal distribution with the variance equal to the learning rate in front of the gradient. So this is how the energy-based models work. And now the authors of the paper actually, with the help of the energy-based models, came up with such an idea that we can reuse, in fact, the discriminative classifier in order to obtain a generative model. So how have they achieved this? First of all, the conditional probability of the discriminative model of the discriminative classifier here can be obtained through the well-known softmax function. So we define the function f with the index y as the white output of our neural network of our classifier. After that, we use delegates in order to parameterize a categorical distribution, and we do that using the softmax function. So we take the exponents and of the function f, and we divide it by the sum over all the values of y of the exponents of the function. And after that, the idea was to reuse these legates in order to define a joint energy-based model. So the joint probability of x and y is now described as the exponent with the energy function that is equal to the negative output of our neural network divided by some unknown normalization constant. And this normalization constant is now really hard to compute, because if here we could compute the denominator, because we had because x was a fixed constant, we could just summarize over the all values of y. This time x becomes a variable, and that is why the z of theta cannot be computed. After that, since we have obtained our joint probability distribution, we can obtain the probability distribution over x. And in order to do that, we just marginalize the joint probability distribution over the values of y. And once we have done that, the energy function for the probability of x is different now. So the energy function actually equals to the negative logarithm of the sum of exponents of our function f. And this is how the discriminative image classifier is now turned into a generative network. So here is once again the scheme of everything that is happening. So if we take the softmax from our neural network outputs, we obtain the conditional probability of y given x, which is the standard conditional probability for a discriminative model. If we apply the logarithm of the sum of exponents, we can obtain the probability distribution of x, and actually the outputs of the network can also be used in order to obtain the joint probability distribution. So now the question is, how do we optimize this thing? Because in the case of the image classifier, everything is already well known. We just take the sum loss function, for example, the cross entropy function, we minimize it with regards to our network. So in order to optimize this joint energy-based model, or JEM for short, we use the following property. For the energy-based model, the logarithm of the joint distribution can actually be factorized into the sum of the logarithms of the probability distribution of x and the probability density, the conditional probability density of y given x. So in order to optimize the generative model, we can separately optimize the loss function over the probability of density of x and the probability density of our classifier. So the loss function for the discriminative part for our classifier is the usual cross entropy, and we just update it using the gradient descent. And in order to introduce a loss function for the generative part, we need to rely on the Langevin scheme. So first of all, we sample some x from our distribution. After that, we update our x using the Langevin scheme. And once we have obtained our x, our estimator of x with the Langevin scheme, we just compute the differences between the log sum exp of the true x and the log sum exp of the generated x. And this is how we obtain, and our loss function now becomes a sum of the discriminative loss function and the generative loss function. And then we can just obtain the gradients for the training. One thing I would like to note is that the scheme presented here for the sampling and the updates of the axes is a little bit different from the standard Langevin scheme. The difference here is in the variance of our random variable epsilon. So here the variance of our epsilon is equal to sigma, and the learning rate is equal to alpha. And if we recall the standard Langevin scheme from the energy-based models, the sigma should be equal to our learning rate. In the paper, in order to train the GEM, the authors actually have decreased the variance of our epsilon of our random variable by a factor of 10 from the learning rate. So sigma is actually alpha divided by 10. And the authors have trained the model successfully, and the results have been presented on the dataset of named CIFAR10. So here we can see that the GEM that I talked about earlier is actually able to achieve accuracy that it can be that is actually on par with the accuracy of the discriminative model, WIDERISNet, which was used as a base classifier. And it is also able to have the inception score close to the state-of-art generative networks. And in the upper part of the table, there is the comparison between the hybrid models that were trained before the joint energy-based model. And we can see that it mostly outperforms all of them. One other thing that came quite handy from training the joint energy-based model is calibration. So what is the calibration of a classifier? A classifier is calibrated when its error rate is consistent with the probabilities it outputs. So for example, when a calibrated classifier predicts the label with confidence of 0.9, it should have 90% chance of being correct. Modern days discriminative classifiers can be quite uncalibrated. So for example, a classifier might output the wrong label with a very high probability. And in some cases, such behavior is quite unpleasant. For example, if we are classifying some images of the road and a network confuses a pedestrian with something else, this can cause an accident. And the metric for calculating how well a classifier is calibrated is the expected calibration error. And the idea behind calculating this metric is actually that we split the probabilities, the output probabilities of a classifier into bins. So we have m bins, and for example, the low probabilities are put together into the one bin and the high probabilities into the other. And this is how the expected classification rate is computed. and we can see that the ECE of the GEM model is far better, is better than the ECE of the baseline model of the WIDRESnet. And actually the classifier, and actually our generative model, when applied to classification, has better calibration than just the discriminative model. And lastly, I would like to present the samples from the CIFAR-10 and the other data sets. The other data sets, I believe, contains the numbers of the houses that are on the tablets on the streets. So, and the samples of on the left are samples from the CIFAR data sets. And actually, all the images on CIFAR are unfortunately fortunately or not, they are of a smaller size, and this is why the images in here are also quite small. But we can see that the samples from both of the data sets actually look quite like the real data. And in conclusion, so I would like to remark that the joint energy-based model is a novel reinterpretation of a standard classifier, and it retains the strong performance of discriminative models and also adds the benefits of generative modeling approaches. However, the energy-based models can be very challenging to work with, and while the authors presented the report on how they trained the classifier, they said that they had to retrain the model several times because the Langevin scheme is quite unstable, and because we cannot actually compute the normalized likelihood, it is hard to tell whether the learning is taking place at all. So that is all for today for my presentation. Thank you very much for your attention.
Okay, thank you, but you severely outfit the 10-minute schedule. The first question, how many Langevin steps did they use?
They used about 50 steps.
50, okay, and how do they actually tune these parameters? I mean, all these alphas, etas, sigmas, to what criterion they looked, how do they tune them?
So I believe that the authors mentioned that the tuning of hyperparameters was really hard, and they basically relied on, so they tried to increase or decrease, for example, the learning rates or the variance of the random variable. And once they increased the variance of the random variable, the model stopped producing a reliable classification score. And so basically this was very much an empirical hyperparameter estimation, and because it is hard to actually tell by the loss function for the generative part of the network whether the training is taking place at all. So basically they spend a lot of time hand tuning these parameters.
Okay, understood. Any more questions to Olga about energy-based models? Okay, if no, thank you. So this was the last talk for today. As some concluding remarks, I would like to say that, well, it's a pity that you're not so involved into discussion of all the presentation, all the papers. I'm sure that you actually have had questions because, for example, for me, some details of the algorithms that were presented were not clear from these short presentations. So I hope that next week in the next series of presentation, you will be more active in asking questions. And the second thing is about the time schedule. Today we have some space for enlarging for discussion or for presentations, but next week we will have 12 presenters, and I ask for all the presenters for the next week to be quite concerned about 10-minute schedule and not to and be ready to fit into the schedule, because otherwise we would not be able to discuss all the presentations without a rush. Okay, so thank you for today, and see you in a week with the next series of presentations. Okay, bye-bye.
Goodbye.